It's going to be easiest if I hold it.
All right, next up we have Amy Tuson, who's going to be talking to us about tess asteroids, a Python package for asteroid photometry with tess. All right, take it away whenever you're ready.
Thanks, Laura. Can everyone hear me okay? Is this microphone high enough? Okay, great. So yeah, hi everyone. My name is Amy Tuson without the C. And I'm a postdoctoral researcher working at NASA Goddard. I'm really excited for this opportunity to present tess asteroids. So this is a Python package I've developed to facilitate asteroid photometry with the tess mission. So I'll give a quick introduction to the tess mission. So tess is an all-sky photometric survey designed to discover transiting exoplanets. So tess has 4 cameras, each of which has 4 CCDs, and it has a large combined field of view that extends right the way from the ecliptic plane to the ecliptic pole. So tess observes the sky in a series of 27-day long observing sectors, and during this time, it provides almost continuous photometry for its entire field of view. So the bottom plot down here just shows a summary of the data products that are delivered by the tess mission. So we have full frame images for the entire instrument field of view, as well as for a pre-selected sample of stars, we have image cutouts called target pixel files, as well as science-ready light curves. So although tess was designed to discover exoplanets, it's also incredibly valuable for solar system science. So for example, during Sector 6 alone, tess observed over 17,000 solar system asteroids, brighter than 22nd magnitude. So these are shown here. So you're seeing here 16 full-frame images from all of the tess CCDs, and each colored line represents the path of a single asteroid during that observation. So you'll see a really large concentration in camera 1 because that was aligned with the ecliptic plane. So what can we do with all of these asteroids observed by tess? Well, with the photometry, we can study their rotation period distribution, we can infer their shape, and we can also search for previously unknown binary systems. So there's lots of really cool papers on this topic. So one, for example, Palatal 2020, they published almost 10,000 light curves for asteroids observed during only the first year of tess, sectors 1 to 13. And this just shows a couple of their example light curves where you can see really clear rotation signals. Now, using their results, they showed that ground-based surveys, which is the light curve database in red here, are likely underestimating the number of slow rotators by at least an order of magnitude. So this is highlighting the importance of using tess for studies like this. So thanks to that long 27-day observing baseline, it's able to pull out longer period rotators that are much more difficult to measure from the ground. So to facilitate studies like this, I've developed tess asteroids. So this is an open source and hopefully easy to use Python package, which allows you to make image cutouts and light curves for asteroids observed by tess. So you can see in the top right an animation. So this shows the image cutout centered on asteroid 1980 VR1 as it moves across a tess CCD. And in the lower right, we have the target's light curve. So I'm going to give a brief description about how this works and how we get these data products. But if you're interested, I encourage you to check out the code and also feel free to talk to me about it. So the first step of this process is to retrieve the relevant pixel data. Now, each tess full frame image is 2,000 pixels squared, and each image cube for the whole sector is more than 45 gigabytes per CCD. So to avoid having to download and work with these very large files, we only download the pixel data that is necessary. So that's illustrated here. So you see here the ephemeris of an asteroid across a tess CCD, where only those relevant pixels Yes. Okay. Switch over. So yeah, on the left-hand side, we have this cadence where the asteroid is overlapped with a bright star in the center of the image cutout. But you can see that the background model has correctly separated these two objects, so our resulting corrected flux still has the asteroid preserved in the center. So we then define a target aperture as a function of time and use it to extract the object's light curve. Now, here's a couple of examples. And in these animations, you can see the aperture highlighted in pink. So in that top row, we see a typical slow moving asteroid, which looks pretty point like on the test CCD. And this is the example I've shown up until now. But in the bottom row, we have a much faster moving target, which moves across many pixels during a single test exposure. And you can see the resulting elongated shape of that target. But hopefully you can also notice in the animation the importance of having that aperture that changes with time, because it's able to correctly capture the change in shape of that object to ensure we're recovering its flux. So the last step of this process is to save this image cutout and light curve file, and we do so in a format very similar to the TESS mission data products to ensure that users who are familiar with TESS will have no issue understanding how these products are stored. Now, I've shown you how test asteroids works. Let me show you some of the preliminary results we have so far. So I used test asteroids to create target pixel files and light curves for 402 bright asteroids that were selected from the catalog of PAL-ETAL 2020. And I selected these targets based on the fact they had to be observed during test sectors 1, 2, or 3, and the light curves had to be classified as clearly single-peaked. So this just means the rotation signal in that light curve only has one peak per cycle. So when creating these target pixel files, I did record the computing performance of the software. So perfect. So the average runtime per target to create the image cutout and light curve file was 27 seconds. And you can see in the plot on the right how that runtime scales with the total amount of data. So as expected, as the amount of data increases, the runtime increases because it takes longer to download and process that data. The little donut plot on the left-hand side just illustrates the fractional runtime of each step. The details aren't too important. I just wanted to use it to highlight that by far the most time-consuming steps are the background correction and the data download. So I ran a GLS periodogram on the light curves to measure the rotation period of each asteroid. And I did this for both the light curve from TESS asteroids and the light curve from PAL 2020. So you can see an example here where in the top row we see the TESS asteroids light curve, and in the bottom row we see the light curve from PAL 2020. Now visually they look very similar, and this is supported by the period analysis. So the periodograms are shown in the right-hand panels, and you can see those measured periods highlighted, which agree very well in this case. I've also included the period reported by PAL 2020, which was derived using a different analysis method entirely, and you can see in this case that also agrees with the measured periods. Unfortunately, we're not always so lucky, so on the left-hand side here, we have a case where the measured periods do not agree, and they don't agree with the PAL 2020 value. Now, there's a couple of reasons we think this is happening. So firstly, the light curves look quite different. So you'll notice in this case on the left, we have a gradual decrease in brightness in that TESS asteroids light curve that is not seen in the PAL light curve at all. And we also have different data masked in the light curve, which is going to significantly affect the results from the periodogram analysis. Now, on the right-hand side, we have a case where the measured periods agree, but they do not agree with the PAL 2020 value. So this is just because PAL 2020 also fit for that long-term brightness variation whilst doing the period analysis. And that's something that we're going to be incorporating in our next iteration to be able to pull out those short rotation periods. So we will be doing a global analysis for the period comparison of our full sample of 400 asteroids once we've made these few improvements. And this will be included in an upcoming paper, so stay tuned for that. But I just wanted to highlight one more thing, which is TESS asteroids can actually be used for any solar system object that moves through the TESS field of view, not just asteroids. So we applied it to the recently discovered interstellar object 3I Atlas, which was observed during TESS sector 92. So you see on the left, those image cutouts with our apertures again highlighted in pink, and on the right-hand side, that resulting light curve. So we recorded a gradual increase in this target's brightness over time as it approaches the inner solar system, and this was consistent with other contemporaneous observations. So that is all I will say about that, but please check out the paper and ask me more about it if you're interested. So yeah, with that, I will leave a summary here. Thank you so much, and I'm happy to take questions.
All right, any questions for our speakers? Well, speaker. There's one at the back behind you. And please may our next speaker come down as well. Oh, it's a virtual one. I should have known that.
Hi, Colin Chandler, University of Washington. This looks really amazing. I've kind of two questions actually. One is, are the error bars just so tiny we can't see them? And the second one is, what is the longest period that you believe that you've seen so far?
Yes, great question. So yes, the error bars are not plotted on this diagram right now. Some of them are very small, some of them are much bigger. That's a good point. I can get you that information with the error bars there per point. We have done a study of like the single point photometric precision of our light curves, and I can also show you that later. But we found that our light curves at the bright end, we have higher precision than the PAL 2020 light curves. At the faint end, we have a little issue right now based on our aperture definition. So we're just going to be refining that to make sure that we're doing better over there. And then your second question was
It's the longest period you've seen so far.
the longest period. Yes. So I'll go based on the sample of 400 asteroids I'm using from the PAL 2020 catalog. The longest period in that sample, theoretically, is 270 hours. That asteroid does not have a clear visual rotation signal. When you look at the light curve, you cannot pick that out. The periodogram does pick it out very clearly. And there are in the full sample many asteroids that have rotation periods that long. So it's interesting to see that TESS is finding these. I think it will be good to run these kind of bulk comparison studies on more sectors. As I said, the original paper was just sectors 1 to 13. We're now over sector 100. So if we can keep running this and pulling out these longer rotation periods, we might be able to build up a sample of slower rotators that we can study.
Awesome. We've got time for one more quick question. Anyone wants to jump in? Oh yeah, we do have one.
Hi, Henry Shea. Hello. Hi, Henry Shea, Planetary Science Institute. This is great. You mentioned that you picked asteroids with a single peak light curve.
Yes.
But generally, asteroids are supposed to have two peaks. So does that mean most of your periods are supposed to be twice as long, or are these like some biased sample or something like that?
Yeah, so this clearly single peak classification was actually defined by the PAL 2020 paper. They have a column in their database that is a P1 or P2, and they say it's single peaked or double peaked. So I initially chose those single peak rotators, believing that meant when I would run the periodogram analysis, we would naively hope that the maximum power would be the true period and that we wouldn't have those half and double aliases. In reality, I find that is not the case. I've started looking at a comparison of this full sample of 400 asteroids, and we find about 10% of them have periods that are either half or double what PAL 2020 reports. So we are finding disagreements there that perhaps these different methods are pulling out different periods. So yeah, something that I think in the future, we won't be biasing the sample like that. This was just to test the results.
Awesome. Let's thank our speaker again.